In this video, we provide an introduction to chemical bonding. Okay. In prior videos, we have studied how electrons are organized in atoms via the electronic configurations. Now we try to explain how atoms interact with each other to form molecules and compounds. In general, there are three types of bonding, which are ionic bonding, covalent bonding, and metallic bonding. Metallic bonding is a highly specialized type of bonding which is normally studied in higher level courses of inorganic chemistry, and we will not study in general chemistry. However, ionic bonding and covalent bonding are very prevalent and they can be easily introduced at the general chemistry level. All right, the general concept in ionic and covalent bonding is that atoms try to generate electronic configurations that are similar to those of rare gases. In the case of ionic bonding, what happens is that electrons are transferred between the atoms that form the ionic interaction, so that you generate a positive ion or a negative ion, and then the interaction that holds the structure together is an electrostatic interaction between the ions. In the case of covalent bonding, what you actually have is that electrons are shared by the atoms, okay, as opposed to being transferred. Okay, and the force that holds together the atoms in a covalent bond is that the electrons that are shared are attracted simultaneously by the atoms that form the bond. All right, so let's take a look at those concepts in a little bit more detail. Let's deal with ionic bonding first. Let's think about the formation of an archetypal ionic bond between sodium and chlorine. Okay, so let's imagine an idealized process which really doesn't exist in reality, in which you form sodium chloride, which is an ionic compound, a solid, okay, from two gas phase atoms of sodium and chloride. If we look at the electronic configurations of sodium and chlorine, okay, we have that the electronic configuration of sodium is equal to neon, and then 3s1, and that for chlorine would be neon, and then 3s2, 3p5. What we know is that when these atoms are interacting in the ionic solid that we call sodium chloride, they're actually not neutral atoms, but they are ions. Okay, so sodium is actually a sodium +1 ion, and chloride is a -1 ion. Okay, so what is interesting about that ionic structure here is that when you look at the electronic configurations of the neutral atoms, okay, notice that you can generate a sodium plus ion, okay, by simply removing one electron, which will be this one. Okay, and you can generate a chloride minus ion by adding one electron, which will generate this electronic configuration, and that's the same as argon. Okay, so notice how the transfer of an electron from sodium to chloride results in a situation in which both of the resulting ions, okay, have electronic configurations of noble gas. And again, this confers a special type of stability and is something that is really sought after by atoms when they form interactions with other atoms. Okay? Now, in these ions, then you have electronic configurations that are the same as rare gases, and then the force that holds together the ionic compound is simply an electrostatic attraction between the resulting ions. Okay? That electrostatic attraction can actually be well captured by Coulomb's law, which simply tells you what is the energy involved in the attraction or repulsion of two ionic species, okay, two charged species. Okay, so from this law we have that the force holding together this idealized form of sodium chloride will be the charge of sodium, charge of chloride, then some constants, including the permittivity of a vacuum, and divided over the distance separating those two ions. Okay? Notice that something important is that the charges have opposite sign, so the potential here is negative. And negative means an attractive interaction. Okay? Notice that if the ions had the same charge, plus and plus or minus minus, then the potential energy would be positive, which means repulsion. Okay? Right, so that's what pertains to ionic bonding. Let's now review covalent bonding to see similarities and differences with ionic bonding. Right, so the archetypal covalent bond is that formed by, for example, the hydrogen 2 molecule. Okay, so you have H2, and that is the interaction between two hydrogen atoms. Okay, now in this bond, okay, what you actually have is that there's two electrons in between the atoms generally. Okay, the electrons have wave functions that can be delocalized, but there's a non-zero probability that the two electrons are in between the atoms, and therefore they can be simultaneously attracted by the nuclei of those two atoms. Right? So if those two electrons are in between the atoms, they can be simultaneously attracted by the nuclei, by the protons in the nuclei, and that is the force that holds the molecule together. A way to visualize this interaction is actually via the drawing of something that we call a potential energy curve. Okay? A potential energy curve is a diagram that looks like this. Here we're going to plot the energy of the interaction as a function of the distance between the two H atoms. Right? So if we go to long distances between the two H atoms, okay, what happens is that those atoms, if they're sufficiently far away, they will not be interacting with each other, and then the energy will be zero. Okay, so this is the asymptote when those atoms are infinitely separated. And again, at large separations, there's actually no interaction between the atoms. Then you get to a point in which the atoms are sufficiently close that the electron of one of the hydrogen atoms can start to be attracted by the nucleus of the other atom, right? So here you have the nucleus, which is positively charged, and again, at some critical distance, you're going to be able to see the interaction with that electron, and the same thing will happen right here. Okay? Because that is a stabilizing interaction, then what happens is that the energy starts to drop, and it will become negative. Okay? As those atoms get closer and closer together, then this cross interaction will be increasingly stronger, until you get to a point where the interaction that you see right there happens to be maximum. Okay? That is the most stable distance between the two atoms, and that is what we call the equilibrium distance. For H2, this equilibrium distance happens to be 0.74 angstrom. Okay, great. Now, what happens if we get to the equilibrium distance, which might be represented by this situation, and then we decide to continue to bring the atoms together? Well, if we continue to bring the atoms together, what happens is that the atoms will be sufficiently close that the protons in the two nuclei start to repel each other, such that the energy actually turns over right here. And then if you have them become very, very, very close to each other, then they will start to actually repel each other, and it's quite possible that you will get a situation in which there's repulsion. Okay, so this is what we call a diatomic energy curve, and you can see how the formation of a covalent bond takes place. Again, this formation of a covalent bond is simply due to the simultaneous attraction of the electrons involved in that bond by the nuclei of the atoms that are forming the bond. Okay, so in this video we actually have introduced the concepts of ionic and covalent bonding. Okay, the main differences is that in ionic bonding you have the transfer of electrons from an atom to a different atom to generate ions that then interact electrostatically. In the case of a covalent bond, there's no transfer of electrons. Instead, the electrons are shared, and the force that holds together the molecule is the simultaneous attraction of the electrons that are shared by the nuclei of the atoms that are forming the bond.